In this video, we're going to do an example of a question involving the Arrhenius equation. So we're told it's a first order reaction, N2O decomposing into N2 and O2. We're told the rate constant at 270 degrees Celsius, and we're also told the rate constant at 350 degrees Celsius. We know from our notes that the temperature needs to be in Kelvin. So that's one of the first things we're going to do is change that into Kelvin. And we're asked to find the activation energy for the reaction. Okay, so the Arrhenius equation, which I showed you in the notes and in another video also, how we can take Arrhenius's equation and turn it into this. Okay, so the natural log of k equals the natural log of A, that's the Arrhenius constant, minus the activation energy over the universal gas constant times the temperature. Okay, and we can write this out twice. We can write it out for the reaction at 270 degrees, and we can write it out again for the reaction at 350 degrees. Before we do that though, I'm just going to pull the important information out of the question. So the rate constant is given at 1.3 times 10 to the power of 11 inverse seconds. Now if this is the unit for a rate constant, that tells me it's a first order reaction. It also tells you in the question, but if it didn't tell you that in the question, you'd know it from the units. Okay, and that's at 270 degrees Celsius. I'm going to add 273 to that to turn it into Kelvin. And the rate constant was 4.5 times 10 to the power of negative 10 inverse seconds at 350 degrees Celsius, which is 623 Kelvin. Okay, now I'm going to use this equation for both situations. So this might take a couple of videos. It's kind of a time-consuming process. But the log of k, and the first k was that. I'm just going to leave the units out for now. It just makes it kind of messy. Equals the natural log of A minus activation energy over the universal gas constant multiplied by the temperature in Kelvin. Okay, and I'm going to we're going to do it for the next temperature. And this temperature was 623 Kelvin. Okay, now we know that the natural log of A is the same in both situations. It's the Arrhenius constant. So we're going to rewrite this to get rid of natural log of A. So we're going to combine these equations and get rid of this term. And how I'm going to do that is I'm going to subtract the larger equation by the smaller equation. I'll do that in the next video.